Okay, so I wanted to talk about a new technique for integration. This one is called partial fractions. And if you think back to chapter 7, we've had a couple different techniques for integration when all else fails or when there isn't an obvious formula to fit it into. And I think the first one we did was substitution. The more recent one we did was integration by parts. And those are much bigger topics than this one. This is partial fractions, and this is kind of a rare case. This is sort of, I would think, of if all else fails, think of partial fractions, but it's usually not the first thing on your checklist that you would go to. So to explain partial fractions, I'm going to go back to an old problem from probably an Algebra 1 class or something like that, where I ask you to add two fractions, and the fractions have expressions in the denominator. So maybe I have 3 over x plus 5 over x plus 2. And how would you do this? You would multiply this side by x minus 2, and this side by x minus 2, and this side by x, and this side by x. And you would get, well, when you did all the things that you needed to do, you would end up getting 8x minus 2 divided by x squared minus 2x. And why is that important? Well, let's say if you had the integral of 8x minus 2 divided by x squared minus 2x dx, you might look at it first and say, oh, maybe there's substitution because I could let u equal to x squared minus 2x, and then the derivative would give me something like what's on the top. And realistically, the way that you would, the easier way to do this one would be using partial fractions, using this knowledge that this is equal to the integral of 3 over x plus 5 over x minus 2. And if I wanted to, because this is how the integration works, I can turn that into two individual integrals. And then this becomes 3 natural log of the absolute value of x plus 5 natural log of the absolute value of x minus 2 plus c. Okay, I only put 1 plus c because I could have put plus c1 here, and I could have put plus c2 here, and then I could have combined those together to make it a c3. But just in the shorthand way we do it, you'd get that answer. We just put 1c to capture the effects of both of the individual constants there, and boom, that's why partial fractions was helpful. However, what maybe you may still be asking yourself, rightfully so, is what would I have done if they gave me this question, but I didn't start by doing a simple fraction addition problem? And that is a good question. So addition of fractions is like, it is a two-way street in math. Like every operation has a way it can be undone, but you don't generally see this process that is called partial fractions, but it's the opposite of adding fractions together. It's decomposing one fraction into two different fractions. And so let's think, for example, if I'm given a problem like this, the integral of 4 over x squared plus 5x minus 14. And I think of all the different things I could do. I think of substitution. Substitution doesn't work. I think of integration by parts. Integration by parts won't help me here. And I think, what else could there be? And partial fractions comes up in my mind. And then I'm thinking, oh, well, partial fractions, oh, well, this equals 4 over x. Geez, does that factor? X plus 7 times x minus 2. So I could think of, well, if I had a over x plus 7 plus b over x minus 2, what would that look like? What would the a and the b be? And what you would think is, well, I'm going to have to multiply a by x minus 2, and I'm going to have to multiply b by x plus 7. And what I want to get is, when I do those things, I want to get this number here, 4. Okay? And if that part's unclear to you, just think this would be x minus 2 over x minus 2. This would be x plus 7 over x plus 7. It's only going to work if the numerator is the same as the numerator that's in this one right here. Okay, so this, then I go on and I get ax minus 2a is equal to bx plus 7b, not is equal to, plus is equal to 4. Notice there's no x. There's no term with an x in here. So this is only going to be true if ax plus bx is equal to 0 for all x, which means a is equal to negative b. So then I can go over here and I get negative 2a plus 7b is equal to 4. Or I could get 2a plus 7b is equal to 4, which, sorry, this is supposed to say 2b. I'm plugging in negative b for a. I resisted making a to be or not to be joke right there, just pointing out. And then my final answer is 9b. That's not my final answer. My final answer is b is equal to 4/9, which means a is equal to negative 4/9, which means if I want to rewrite this expression here, I can write this as integral of negative 4/9 over x plus 7 . Okay, just making sure I got the right ones, plus the integral of 4/9 over x minus 2 dx, which I could then, let's see, I'll carve out this kind of space for me to work on here. Then I could also say that it's easier to say this is 4/9 the integral of 1 over x minus 2 minus 4/9 the integral of 1 over x plus 7. And so you could say this is 4/9 times natural log of the absolute value of x minus 2 minus natural log of the absolute value of x plus 7 plus 1c that takes care of both of the c's. And then you can really say, if you want, I could call this 4/9 times the natural value of the natural log of the absolute value of x minus 2 minus the natural log of the absolute value of x plus 7. And then I could just like keep this, and I could write 4/9 c, but I would never write the 4/9 because c is still just an arbitrary constant. And that's your answer. That's how partial fractions work. It's a little bit of legwork, but I think the process is intuitive. And the other thing that I would say is that for this particular example, I'm pretty sure another way you could write it, and you wouldn't have to do this, but if it was a multiple choice question, you would have to know that that's a possibility, is because natural logs have that property where subtraction turns into division. You could rewrite it as the natural log of one fraction right here. Okay, that's my video on partial fractions. It's a new tool for your tool basket. I hope you find it useful at some point in your life, like today.